So today we are going to study about whom we'll study about convection. Till now we have finished what conduction. We have also studied radiation. We have also studied what is heat exchanger. So now let us try to understand the very important part of this topic, heat transfer, that is convection heat transfer. So let us try to understand what is the mechanism of convection. Okay, so first thing we are going to understand today is that what is the mechanism itself of heat transfer, like convection heat transfer specifically. That what do I mean, that whenever I say that there is some convection heat transfer, then what is the physical meaning, and then we will understand that how to find the rates and what are other variables we'll be able to see. Okay, so let me just hide it first. Yeah, now so see what happens in the convection. What I have written here is that mechanism of convection. So what happens in the convection heat transfer is, first thing is that there will be, like let us say that I am talking about this figure A. Okay, so what we can see here is that there is a surface, right? And on this surface, like let us say that this surface has got some temperature 50 degrees Celsius, and then I am blowing some air upon it with the help of a fan. Yes, and the air has got some velocity, let us say this is 5 meter per second, and it has temperature of 20 degree second. Then what happens is that whenever there is some flow happening, then this flow will come into picture, right? And they will come to this parts of this heated surface, and then what happens is that this air which is colder than the hot plate, what they will do is that they will pick up the heat, and since it is a continuous flow, then what happens is that this air will travel in this direction, and then again some fresh air will come and they will pick up the heat, and then they will transfer. So this mechanism continues. So this is what the physical mechanism what happens in the convection, that every time what do we have is that there is a surface, and upon that surface there is a what bulk fluid motion. We name it bulk fluid motion. So there is a fluid which is having some velocity, comes into picture, picks up the heat, and then the next one comes into picture. But here my mechanism to provide the velocity to the fluid, for instance here fluid is air. So what is that? This is by a fan. Can we this the external source of the fluid? So that's called convection. Fine. Now let us look at this figure B. So here what happens is that, can you see there is no fan or any other thing which is helping this air to come into this picture, but this is due to what? Due to the buoyancy effect. What is happening here? Due to buoyancy effect. And what is that effect? We have discussed it earlier in the very first class. And what happens here is that whenever air is hot, we know that PV is equal to mRT, and from this one we know that P is equal to PV is equal to M upon E is nothing but rho RT. So can you see that rho is E upon RT? So can you see that whenever your temperature increases, what happens? Your density increases. That means it becomes lighter. So whenever the air is lighter, it will rise up, and when it is trying to rise up, then what happens that any air, like let us say that the air in the close vicinity to this free convection, that to this plate, what happens that any air which is in close vicinity to it gets what? Higher temperature, means which is in this vicinity, will get heated, right? And once they are getting heated, they are becoming lighter and they rise away. And once they are rising, the other air, like can you see here there are two arrows here, here. What happens is that once they are what rising away, they are creating some space for other fluid to come in, and then other fluid will come in, and then they will rise up. And what happens in this mechanism is that every time air is coming here into the picture, and they are picking away the heat and they are rising. So this is what free convection, because you are not trying to provide any external source to cause the flow, but this is rising to what buoyancy effect. Okay, and now this is forced convection, this is free convection, and then you would want that is there any conduction also? Yes, there will be conduction. Like let us say that there is your flat plate here, and it is having, like let us say, same heat 50 degrees Celsius. Okay, and since there is no significant sometimes temperature difference, let us say that your air is at 40 degrees Celsius and this air is not flowing and the temperature difference is also not significant, then what happens in that case is that this flat plate will be losing heat due to only what? Only due to conduction. Like here there will be a very stagnant layer, then this will be losing heat to this stagnant layer, and in that manner it will be losing heat. What I am trying to say is that there will be a very small stagnant layer of air here, and this there will be very small stagnant layer of air here, and this plate will be losing heat to this layer due to what? Conduction only. Why? Because this is stagnant. Since there is no motion, then there cannot be any convection, so that is why I have written no convection currents. Fine. Now, so let us understand that then how this conduction this convection happens in the real. See, here what I have shown you is that your plate was heated, right? Let us say, for example, that my iron block is there and it is having temperature of 400 degrees Celsius, and let us say that again air at 30 degrees Celsius, for say that this is coming into picture. Then what happens is that here what happens is that this layer, there is a layer which comes into picture and attains the velocity of the plate, right? And due to what? Due to no slip motion. So let us say that if this plate is stagnant, then in the very close vicinity, what happens that there is some stagnant layer. Okay, it keeps on moving after some time, but there is one stagnant layer. Okay, for that extent, then what happens is that my plate will first lose by heat by conduction to this plate, and then this heated, like you are conducting heat from this surface to the outer surface, like here, and then your air comes in and they are picking away the heat. Then this air becomes hot cooler, then again you are conducting heat, this comes away and picks up the heat. That means here we can say that conduction and convection both are happening simultaneously. Why? Because can you see this arrow? So what happens here is that I am losing by heat by conduction to the surface, and then from this surface convection is taking away the heat. That is why I can say that there is always conduction and convection happening simultaneously. Similarly here, let us say there is a hot plate whose temperature is 110 degrees Celsius, and there is a cold plate whose temperature is 30 degrees Celsius. Then what happens is that then your fluid is flowing, right? So what happens here is that there is a pickup of heat from this point, and then this pickup of the heat will travel to whom? To the colder plate, right? So can you see that here again the fluid velocity has helped you to achieve the heat transfer. So now my idea is that why convection is necessary. See, what happens is that your convection heat transfer is able to help you to convey more heat. Why? Because every time we have fresh molecules to pick up away the heat. But in case of conduction, there is stagnant layer. So once they are heated, they are not traveling away from that point. Then what happens is that you are not able to conduct more heat to that particular stagnant layer, right? So that is convection is helping you that they will come, they will pick up the heat, and then again they come, they will pick up the heat. In that manner, I am able to lose more heat. So this is the idea of convection. Okay. Now, So like we have seen conduction equation, right? So in conduction we have seen that q was minus of k dt upon dx, and then we realized that this is the k who is the one here decides that what is the heat transfer rate basically. So now here what happens is that similarly here we have, like we have k in case of conduction. So here what do we have is h. What do we write about q in the convection is that q dot convection. Q convection is nothing but h multiplied by surface area into delta t, right? But here who will be deciding that the rate of heat transfer h, and what is this h? The function of h itself is the function of whom? It is the function of velocity. It is the function of what? Characteristic dimension. It is the function of density. It is the function of viscosity. It is the function of specific heat. It is the function of thermal conductivity as well. So can you see, unlike conduction, this is not the material property. Why? Because this is varying with the change in velocity, dimension, density, and other factors. So these are the properties called thermophysical properties. So these are what? Thermophysical property. Okay. Now, so then you will have to find out that what is this h, what is the dependency upon these two for a given flow. Then only you will be able to find out the rate. Now, why? Because unless you find h, you cannot find q. So in order to find q, you will have to find h, and h is dependent upon so many factors. So what dimension analysis does is that they will they will group these given thermophysical properties into some dimensionless numbers, okay, and then I would say that my h is dependent upon those numbers, and then I would look after the relationship between the h and those numbers, and then I will say that okay, I am now able to do my what, this analysis. Got the idea? So let us try to find out what is this dependency, okay. So here I have introduced one word that is called d. And what is d here? D is the characteristic dimension. Okay, characteristic dimension of the body. Okay, characteristic dimension of the body. So what is this characteristic dimension of the body? D. This is equal to 4 times of cross sectional area, like 4 times of cross sectional area divided by the perimeter. Divided by whom? Perimeter. Like let us say that you have a circular pipe, and inside this you need to analyze what is the force or any convection heat transfer. So in this pipe, like force particularly I am talking about. So what happens in this one is that what is the area of this circular pipe? This is cross sectional area. So A of what? A is the cross sectional. I am writing like this, cross sectional area. Okay. So can you see here that 4 into what is the cross sectional area of the circular pipe? Pi by 4 d square. And what is perimeter? In the case of like flat plates, for the case of flat plates, for the case of flat plates, this is the length only. Like let us say this is a flat plate upon which there is some flow is happening. Then I would say that what is the L? L is the length of body itself. What is L here? L is the length of body itself. So this L which you can see here now, this itself is the characteristic dimension. What is this? This is the characteristic dimension. For now I can write it D. Okay. And for circular pipes we have seen this is the D. So given on the, let us say that sometimes there is a rectangular duct. Then in case of rectangular ducts, what happens? In case of rectangular ducts, let us say that this is A and this is B. Then what is D here? D is nothing but 4 times of cross sectional area, and this is cross sectional area, right? So 4 times of A into B and divided by what is the perimeter? 2 into A plus B. So then whatever is the given, now when you do this dimensional analysis, now when you do this dimensional analysis, then for any post convection heat transfer, post convection, what I'm writing post convection. So for any post convection heat transfer, for each post heat transfer formula, what happens? The number is function of the number is function of what? This is function of this the property dimensionless number. Numbers now become function of what? Random number. So this is the function of number. But the question, what is another number? So I have no idea. Like we try to define the dimensionless or dimensionless. We try to determine the dimensionless groups out of the given properties. We have in properties we have P and 3 sig. Quantity. So then when you go to find out dimensionless growth, and you come across that there is dimensionless growth called, let me state it my. So this is Vd into rho upon V. This is nothing but Reynolds number. Okay. Reynolds number. Okay. And we have another parameter, let us say this is pi, and this is HD upon K. Okay. This is nothing but Nusselt number. And there is one more item. This is how it looks like. Is there is mu Cp upon K. Mu Cp upon K. And this is termed Prandtl number. Okay. So what it is decided with the help of dimensional analysis, that your Nusselt number now, this Nusselt number, like your phi 2 is function of phi 1 and phi 3. Now I can do dimensional analysis, and now I know that where is your H can be visible. H is visible in whom? Nusselt number. So my Nusselt number now signifies whom? That my dependency of H upon whom? Other flow properties. Can I see that? Yes. So now can I write down that this HD upon K, this is the function of whom? Vd into rho upon mu, and second thing is Cp upon K. So now I can see that I have formed a group of numbers, and I can see that how my H is dependent upon the flow properties. Got the idea? So this is one case. Okay. Now, so let us now quickly understand these numbers. We have came across which numbers? One is Reynolds number, one is Reynolds number, one is Nusselt number, and one is Prandtl number. So let us try to understand them. And these numbers are the one which we are going to counter in this force convection analysis. Yeah. So now we have moved to home force convection analysis. So first is Reynolds number. So what is Reynolds number? Reynolds number. So what is Reynolds number? This is the number who signifies the ratio of inner So it is the ratio of inertia forces to viscous forces. So when you go on writing what is the magnitude of inertia and viscous forces, then this ratio comes out as rho v d upon mu. Okay. And what is rho? Rho is density, v is the average velocity, d is the characteristic dimension, and mu is the dynamic viscosity. So one thing I know, Reynolds number now. Okay, so what this Reynolds number signifies, that it decides the what will be the nature of the flow, like it will be laminar or turbulent, will be decided by whom? Reynolds number. And what is the critical Reynolds number for pipe flow? For pipe flow, you know the flow nature also. Why? Because with the nature of flow, you value will change. So dependently on the like Reynolds number or Prandtl number. So Reynolds number that is less than 2000 or let's say 2300 in some they have written 20 but 2300 is the best. So what do I event that my number is less than 2300 and say my flow is less, and it also is greater than it is between 2300 to 4000, then I say that my flow is in transition state. Okay, I am talking about my flow, and when your Reynolds number is greater than 400, then I 4000, then I say that I have entered into turbulent flow. Okay. Similarly, for flow over flat plates, what happens is that your critical Reynolds number is that, like if your Reynolds number is less than 5 into 10 to the power 5, then I say that my Reynolds number is laminar. Oh no, it's my nature is laminar. Okay, so we should find these values now. So Reynolds number, the idea of Reynolds number is clear, that that what is the nature of flow. Okay, what is the meaning of laminar and turbulent flow? In the laminar flow, the intermixing of fluid is absent. Like if the fluid is flowing like this in this nature, then the intermixing of fluid between these two layers is absent. But when I say that the flow is turbulent, then what happens is that like the intermixing between the layers is present. Okay, so what does it mean? That the intermixing between these two layers is present in the turbulent flow, but in the laminar flow they are flowing in this direction only, there is no flow in these directions. Okay, now so Reynolds number now I understand. Yeah, so let us now try to understand Nusselt number and Prandtl number. So next dimensionless number is Nusselt number. Nusselt number. Okay, so what is this Nusselt number? This is the this tells you that which one will be dominating. Like you can have conduction and you can have convection also. So the Nusselt number is the one who helps us to decide that what will be the dominating one. So this is the ratio of nothing but Nusselt number is nothing but ratio of, this is the ratio of how much heat I am able to conduct and how much heat I am able to convect. So Q convection upon Q conduction. So in order to have dominating convection heat transfer, then what happens is that my Nusselt number will have to greater than 1. If my Nusselt number is equal to 1, then heat transfer is by whom? Only convection. So then heat transfer is by conduction only. Okay. Okay. Now let us try to find out this ratio, that how this ratio would look like. So can you see that your conduction heat transfer, like your conduction heat transfer, we have seen that this was nothing but K into dt upon Tx, like per unit if I am willing to write. So can I write down this is K into delta T upon L for a given length? Yeah. And what is Q convection, Q per unit area if I am talking about, and can I write down this is H into delta T? Yeah. So these two I know that this is whom, this is convection and this is for conduction. And then when you take the ratio of these two, then how your Nusselt number would look like is that we have conduction as K into delta T upon L, and here we have H into delta T. So this delta T and delta T got cancelled out. So can I see that this is H multiplied by L by K. So just now we have seen now that Nusselt number was HL upon K. So what this Nusselt number is trying to signify is that what is the mechanism of heat transfer which will be dominating, and in order to have the convection heat transfer, then what you will have is that your Nusselt number is must be greater than 1, and if your Nusselt number is greater than 1, then this is by conduction only. Got the idea what is Nusselt number and the physical significance of it? Got it? Okay. Now, so Nusselt number we know Reynolds number. There is one very important phenomenon, Prandtl number. So Prandtl number we will a little bit later, just a bit later. So let me help you few things, and then you will understand that how you will see the what Prandtl number. Yeah, Prandtl number is there, right? So Prandtl number will come to this number just in few minutes. Okay. So before that, let us try to understand few things. So let us try to understand like flow of flat plates. Like we have what kind of flows we can have, that the flow is of happening over a flat plate, or the flow is happening inside a circular, right? So let us first analyze flow over flat plates, and more specifically I'm talking about whom, force convection. Okay, so whenever the fluid is flowing over a flat plate, then there is a hydrodynamic boundary layer made upon that. Hydrodynamic boundary layer is always formed. So what is this hydrodynamic boundary layer? Let me help you to understand that what happens that whenever there is a flowing fluid with some velocity is coming into the touch with a flat plate which is stationary, or maybe it can have some velocity even, then what happens is that the fluid layer which will be in the touch of the fluid layer, can you see that here the bottom layers which will come into contact with this flat plate, the bottom layers which will be coming into the contact with this flat plate, then they will also assume the velocity of whom, this flat plate only, due to what, no slip condition. No slip conditions means what, that there cannot be two velocities existing at the same point. Okay, so there will be no slip. That means that this fluid will attain the velocity of this surface. Then can you feel that these fluid layers which were coming into picture, all of them were having some velocity, but my layer which has come into contact has got its velocity as 0. Then what happens is that if this velocity is 0, then the layer above it will also what, due to inertia effect, they will also lose some velocity, and so on. So what happens here is that in this direction you will feel that your velocity gradient is existing. Earlier the fluid velocity was uniform, but now since this velocity has got decreased, then this will decrease the further fluid layers velocity, and when the this what, diminishing effect of velocity, like when the reason, there will be a reason beyond which which you will feel that the velocity is same as the earlier one. Like if I say this is the free stream velocity, then there will be a region defined here beyond which this velocity will not change. This velocity will remain only the previous one, but now there will be a region into which there will be a velocity gradient existing. So that is called what? Like this region which you can see now, this is nothing but that boundary layer into which I can see some velocity gradient. Got it? What is velocity boundary layer or hydrodynamic boundary layer? Okay, this is one thing. Now second thing is that this boundary layer will keep on increasing in the direction of flow. Why? Because if this has got lesser value, then this will keep on reducing its velocity. Okay, so if this has keep on reducing its velocity, that means my effect of velocity in this direction, like velocity due to the what, no slip condition, the gradient which I was feeling earlier here, this effect will be felt at higher distance in the direction of flow. So then I can see now that with the direction of flow, like with the increase in the length in the direction of flow, I can see that my velocity boundary layer is increasing simultaneously. One thing. And second thing now is that the flow inside this boundary layer, is rotational in nature, okay. Okay, one thing. And second thing, if this is rotational in nature, then you cannot apply boundary layer Bernoulli's theorem into it. Okay, Bernoulli's theorem you must know. Then there were certain assumptions, and one assumption was that the fluid is irrotational, but in this region the fluid has got some rotational velocity. That is one. Again, can you see that your boundary layer has got increased from the laminar flow to the turbulent flow? I can see that my thickness has also increased, and another thing is that this profile has also got changed. Okay, two things. And then there will be one transition region. So this is what region into which that your flow is trying to change from laminar flow to the turbulent flow. Okay, so this is all about what? Hydrodynamic boundary layer. Got the idea? And what is this region? This is till this point, what is your Reynolds number? This is 5 into 10 to the power 5, and this is your transition region. So here you can take it even 7 into 10 to the power 5. Okay, so your Reynolds number is 5 into 10 to the power here 5 here, and Reynolds number is equal to 7 into 10 to the power here, and this is your transition zone. Okay, now so can you see one more thing here, that if we know one property that is called kinematic viscosity. So what this kinematic viscosity is trying to tell you is that how quickly you are diffusing your velocity. Got the idea? So if your kinematic viscosity denoted by nu, if this value is higher, then it will be able to quickly diffuse its velocity. Then what will happen is that your thickness of boundary layer will increase. Why? Because if it is quickly diffusing, then the presence of this boundary layer will be felt to the higher regions in the direction perpendicular to the flow. Got the idea? So if I say that if this is the V and then there is one more V, let us say this one, then for the same distance, like let us say this is X and this is also let us say X, then if V is more, then my boundary layer thickness will also be more. Like here your V is lesser, that is why your boundary layer thickness is also less. Got the idea? So kinematic viscosity is helping you to understand that how quickly you are able to diffuse the velocity. If you are quickly able to diffuse the velocity, that means if you are quickly diffusing the velocity, what is that meaning? That you are adapting the situation very quick, okay? And then this difference will be felt till what? The higher regions, okay? So what is this region defined? So at these points, what do I say? That the difference between velocities, like let us say, what is the delta? At delta, this thickness is termed as delta. So what happens, that inside this region there is velocity gradient, but at delta v is approximately, like let us say that in this region this is defined as v, then v is approximately equal to what? U infinity. For this case u infinity is written there. So u infinity means that the velocity of free stream, okay? So what is the catch here is that you should know that how this boundary layer is defined, and at this point, like this is not exactly equal to, but this is equal to what? 0.99 times of u infinity. So can I say that if my velocity at delta, like what I'm trying to say is that at delta my velocity is equal to 0.99 times of whom? U infinity, then I can say that I have my boundary layer is was till this region, and beyond this region there is no effect of this boundary layer, right? So boundary layer effect is felt till some distance in the vertical direction, and what is defined that, let us say if I am writing delta, so this is what? Boundary layer thickness. Boundary layer thickness, okay? So now I understand what is boundary layer thickness also, okay? So similarly, like we have seen hydrodynamic boundary layer, so similar will be case when you are trying to analyze it thermally, okay? So what is thermal boundary layer now? Likewise, you have seen now that the no slip condition was existing at the point of what? Contact, where the fluid comes in contact with the plate. So similarly here, let us say that there was a free stream whose temperature was T infinity and came into the picture with whom? Whose surface temperature is, let us say, Ts. And let me say that my Ts is less than T infinity. My surface temperature is less than the free stream temperature. Then what happens? Again here the two temperatures cannot exist, right? So what will happen is that this free stream will assume the temperature of whom? This surface temperature which is in contact, like the layer which is in contact. The layer which is in contact will assume the temperature of the surface, and here what do you have? That just now we have seen now that after some reason this effect will not be felt. That means you have T infinity at some reason. Then what do you see? That here you have less temperature, and then this temperature difference is increasing. Can you see that this is slowly, this Ts is slowly approaching whom? The free stream temperature. Can you see that this temperature Ts is slowly or what I can say that this fluid layer which has came into contact is slowly approaching whom? T infinity. So that is why what is my profile looking like here is that I am trying to increase my temperature. Then again the point where you feel that that you have reached the free stream temperature, then the thickness at which you felt that I was able to, let us say that at this thickness you felt that your temperature is nothing but the surface temperature, like free stream temperature only. Then what do you name that? This is nothing but delta T, also called as what? Thermal boundary layer. What is this? thermal boundary layer thickness. Thermal boundary layer thickness. Got it? What I am trying to say is that as the case of hydrodynamic boundary layer, we have seen there was boundary layer thickness or hydrodynamic boundary layer thickness. Similar is the case with the thermal boundary layers also, means thermal flow. So what happens in that case is that in the thermal boundary layer again there will be temperature differences felt, but at those surfaces, or not surface, at those distance in the what direction perpendicular to the flow direction, where I would feel that my temperature of this stream is equal to the free stream temperature, then I would say that that is the point your thermal boundary layer has vanished. There is no thermal boundary layer effects felt. Got the idea? So similarly, let us say that anywhere, let us say that you were talking about this point, then at this point what is delta T? So this can keep on changing and will keep on increasing. Okay, so this is what hydrodynamic and thermal boundary layer is. Then there is one question, that one is thermal boundary layer thickness, one is delta T, and one is what, delta simply. So one is thermal boundary layer thickness and one is hydrodynamic boundary layer thickness. Yeah. So now my question is that which one will be more? Yes or no? So you will have to decide which one will be more. Yeah. So in order to decide that, again you should know, likewise in the case of hydrodynamic boundary layer thickness, we decided that the alpha, not alpha, this was whom? This was nu. The kinematic viscosity was the one which was helping you to decide that what will be the thickness of boundary layer. If my nu is more, then I can diffuse more velocity, that means I can increase my thermal boundary layer thickness. Similarly, then is there any parameter who will be judging what will be delta T? So then I would say yes, there is. And what is that? Alpha. Alpha, do you remember? This is thermal diffusivity. Thermal diffusivity. So now alpha will decide in the case of whom? In the case of thermal boundary layer. Now alpha will decide that what happens with the thermal boundary layer thickness. So now I know what is the thermal boundary layer and what is the hydrodynamic boundary layer. Then let us try to find the correlation between that, how to decide whose thickness will be higher and whose thickness will be lower. So this is the Prandtl number who is helping us to decide that whose thickness will be higher and whose thickness will be lower. So this is the ratio of now whom. This is the ratio of kinematic viscosity divided by thermal diffusivity. So now I know that yes, definitely their ratio will decide. Why? Because alpha is deciding thermal boundary layer thickness and nu is deciding what? Hydrodynamic boundary layer thickness. Then the ratio of these two, if this is less than 1, greater than 1, we will be able to judge that whose thickness will be higher. So let us try to simplify it first and then we will look more things further. So this is nu, and what was alpha? Thermal diffusivity alpha is K upon rho Cp, right? K upon rho Cp, this we have seen earlier. So this is nu and this is alpha is K upon rho Cp. So can you see now that nu is nothing but mu upon rho, okay, and K upon rho Cp. So let us cancel out rho and rho. So this becomes what? Mu Cp upon K. And again, what is this mu? This was the kinematic viscosity, and this is what? This is dynamic viscosity. Okay. This is dynamic viscosity. Okay. So I hope you understand that it is the ratio of what? Kinematic viscosity and thermal diffusivity. Then let us understand one very interesting phenomenon about this Prandtl number. Can you see here what do you have is mu Cp upon K. Can I write this mu Cp upon K? What is the K? K is the property of the given substance. Cp is also the property, and this is dynamic viscosity, also the property itself. So can you see that Prandtl number will also become property only, like other dimensions number are changing with the flow, but Prandtl number, which is the ratio of mu Cp upon K, this is not going to change. This is not going to change. Can you see? This is mu Cp upon K. These values are not going to change. If I neglect the effects, like it can change, like with the flow mu Cp and K can change, but I neglect those effects, then I can say that yes, this is the ratio of properties only. Then Prandtl number itself becomes what? Prandtl number itself becomes a property itself. Got the idea? Okay. Now, okay, now, so Prandtl number. So we have discussed few things about Prandtl number. Now what is the significance of it? It is signifying you the relative magnitudes of momentum diffusion rate. Kinematic viscosity is diffusing what? Momentum, and thermal diffusivity is diffusing home heat energy, right? So these two are simultaneously being diffused, but this ratio will decide that which is diffusing more. Got the idea? So this will happen in those cases where you are having a flow over flat plate, and the what is the case that you are having hydrodynamic boundary layer and thermal boundary layer, they are forming simultaneously. Okay. Okay. Now, so I understand what are these things. So let us now quickly understand that what is the relationship, what is that relationship who will help you to decide that which one value will be more, so that you can just but it is higher. There is one relationship that, and what is that? The delta T thermal boundary layer thickness divided by delta hydrodynamic boundary layer thickness. This is equal to 1 upon 1.026 multiplied by Prandtl number to the power minus 1 by 3. So if you remember this relation, then you can always find out that what are the magnitudes of delta and delta. So let us say my Prandtl number is greater than 1. For example, let me say that Prandtl number is greater than 1. If Prandtl number is greater than 1, what happens with this value? Prandtl number is greater than 1. So let us first write Prandtl number. What was this one? It's the ratio of nu upon alpha. So if this value is greater than 1, then I can say nu is greater than whom? Alpha. Yeah. So if nu is greater than alpha, then what happens? If this value is greater, then delta is greater compared to whom? Delta t. Similarly, what is this ratio? Delta t upon delta is less than 1. Similarly, if you go to home, your Prandtl number is less than 1. This is equal to again nu upon alpha is less than 1. Can you see that your alpha alpha is greater than whom? Nu. Then what happens is that your delta T will be greater than whom? Delta. Yeah. So you can analyze in this manner, or you can remember the relationship also. Both of them will be able to help you to decide that whose the magnitude it will be higher. So questions are very frequent from this area, that they will say you that random number is this, and they'll tell me what is the relative magnitudes of nu and means thermal boundary layer and hydrodynamic boundary layer. So I hope that by this analysis you will be able to guess. Okay, so let us move to the next. Now let us quickly do one small control volume analysis about this thermal boundary layer. So I told you earlier also that what happens here is that I am transferring heat by conduction, just this layer, and then this layer is transferring heat by convection. So there is conduction and convection happening simultaneously. So let us now quickly analyze this part. So what I am trying to do is that if I try to draw a hydrodynamic boundary layer here, so then hydrodynamic boundary layer is something like this, and if I try to draw my thermal boundary layer, then you have seen thermal boundary layer. Now what is this, that your surface temperature is higher. When your surface temperature is higher, then what will happen is that there will be one, like if you are analyzing that, you are trying to look after that what is the boundary layer thickness and other things in this region, then your surface, let us say that this is happening at 20 degrees Celsius, then this is 400, then definitely this is higher. So this layer which comes into contact will assume velocity of 400 degrees Celsius, and after the thermal boundary layer, let me say that this is the thermal boundary layer, this is the thermal boundary layer, then after the thermal boundary layer what would happen is that again your temperature will decrease. Can you see that your temperature is decreasing now? Why? Because your plate temperature is higher, that is why your temperature has to decrease in this direction, and then you will feel at delta not infinity. What? So now it is infinity. So let us now quickly analyze that what is happening here simultaneously. What happens is that I will control equal to 0. This will be equal to heat convected heat convected from the hot plate, from the hot plate to free stream, from the hot plate to the free stream, right, to the free stream. Okay, so now what I can do is that I have minus of kf into dA by dt dA. What is that temperature difference? So what is heat looking for? Can you see it? Minus as 1 by temperature difference. So it is the try. So what is happening here is, on the flow over flat plates, what happens here is that you try to find out what is the temperature distribution. So your temperature distribution is T minus of TW, T minus of TW divided by infinity minus TW. This is equal to 3 minus quantity minus your temperature distribution is case of so here your function is for temperature is function of both one was with x or delta you watching, right, and in fact you can see that we have so you So we find out this is that how we this will be able to check this kind of so delta t increases with the x, yes or no? Delta t increases with the change in what? X. So what happens here is that hx decreases with the change in okay. So can you see that your hx is function of your hx is function of x. Can you see your hx is function of x? And why? Because delta t was function of x. So with the increase in x, what I will feel now, that my hx will decrease. So just now I have told you that with the change in x, my h was decreasing, yes or no? Yes. And then what is the nature? What is the nature? Can you see one more thing is that delta t upon delta is function of whom? Prandtl number. Yeah. And there is one relation for hydrodynamic boundary layer, that boundary layer thickness, this is equal to 4.91 into x upon Reynolds number at that particular x. This is the solution of Blasius, who determine that your delta for flat plate, the laminar flow is 4.91 divided by delta can be directly delta is proportional to square root of 1, because here we have to 1 and Reynolds number is rho v x, right? Because for flat plates characteristic number is less only. So here we have 1 by 2, here we have 1. So 1 minus 1 by 2 is nothing but the power 1 by 2. So can I see that it is directly proportional to x, and this one I see that my delta t is again proportional to whom? Delta. So if delta is proportional to square root to the proportional to x, then we see that delta t is also proportional to square root of x. Here you can see. Can I see this thing? My delta t is also proportional to the square root of x. Also dependent upon that. We complicated it the help of delta t, and delta t is proportional to the square. That means your hx will also decrease the proportional to what? X is proportional to the power minus 1 by 2. Why? Because this is power 1 by 2. Okay. So and you see that your h is now proportional to the x to the power minus 1. Just now I have told you, so this is the explanation for that. Can you see now that your temperature distribution, if you know, then you can find out what is your Nusselt number, right? So Nusselt number is hs into x upon what? Okay. If I know how to write hx, then I can write down my number also. When we saw this one, then what do I So your Nusselt number is function of whom? Reynolds number and Prandtl number, and we are able to judge that what is that relationship, okay? And this is what local Nusselt number, that means, or I can able to find out that what is my local heat transfer coefficient, not over the entire plate. So and what do you put in calculation? Like let us say there is a plate, then what do you put that H? H is the average heat transfer coefficient, but what you are able to determine from here is the local heat transfer coefficient. Then how to find out H bar? Means the average heat transfer coefficient. How to find out average heat transfer coefficient? Okay, so average heat transfer coefficient H bar. So what you can do in order to find this one is that you will go on to that plate, okay, you will go on to that plate, and then what you would do is that you will take a strip, you took a strip, and then what happens is that you try to analyze the flow upon this one. Then you have, let us say this was T infinity, and you have started from, let us say, x is equal to 0, this is x is equal to L, and it has got thickness in this direction, that is B, or let us say this is width, and then your wall temperature is TW at this point. Then what is dq from this strip? Can you say that from dq from this strip will be nothing but hx at this particular x? What is that hx? And let us say this is dx. Then hx multiplied by whom? What is the width? Like area I am trying to write. So b into dx into temperature difference, and what is that? Tw minus of T infinity, right? So now I know what is my dq. So if I know my dq, then if I integrate like dq, I know that this is hx into b into dx into temperature difference Tw minus T infinity. Then if I integrate it between h to L, then I will be able to find out what is my h, in fact, right? So dq is nothing but, what you are trying to do here is that you will integrate it between whom? 0 to L. Got the idea? And then you will find out that what is this q. So can I do one thing, that let me say that this is equation 1, and you will integrate it between 0 to q, then you are able to find out what is q, and then this is done. Okay, next thing is that if I try to write down this q in terms of, if I try to write down this same q in terms of whom, if I try to write down this same q in terms of h bar, then can I write down that q is equal to h bar into area. Area, what is that area? B into L, right? This is L and this is B, then area is B into L. So h into A is done, and what is delta T? Delta T is nothing but Tw minus T. Each like we integrate it and one, the bar into Tw minus T infinity. What I am trying to do here is that equating 2 is equal to 1, then this is equal to integration of 0 to L hx into b into Tw minus T infinity into dx. And then can you cancel out few terms? Yes. What terms you can see? We can cancel out this b is direct cancelable, okay? And this temperature difference can also get cancelled out. So these got cancelled out. So can you see now that, can you see that now I can write that h bar into L is equal to nothing but 0 to L integration of hx into dx. Yes, you can see. Now what is h bar? H bar is nothing but 1 upon L integration of 0 to L hx into dx. Now if you know the variation of h with respect to x, then you can solve it, right? So let us try to solve this equation. Then I know that what is h bar? H bar is equal to 1 upon L integration 0 to L and hx into dx. And just now we have seen how hx was varied. Hx, we saw that it was varying with respect to x to the power minus 1 by 2, right? So can I write down this is nothing but like this one only, into x to the power minus 1 by 2. So when you go and put on this one, then can you write down that h bar is equal to 1 upon L 0 to L and hx is nothing but c into x to the power minus 1 by 2 into dx. Then what is your h look like is h bar is equal to c upon L, and what is this value, x to the power minus 1 by 2 plus 1. You integrate it, right? To the power 1 minus 1 by 2 plus 1 upon minus 1 by 2 plus 1, and limit is 0 to L. And then when you put this one, then you will find out that h bar value, this is now equal to whom? Equal to C upon L multiplied by whom? Multiplied by x to the power minus 1 by 2 plus 1, this is plus 1 by 2 root x, yes or no? And this is minus 1 by 2, this is 1 by 2 only, right? So can I see that this is c root x, and can I see that this is nothing but hx. So can I see that your h bar has now turned into 2 into h of x. No, this is minus 1 by 2 na. So minus 1 by 2 plus 1, this will go on the numerator. And what about this one? Minus 1 by 2 plus 1, this is plus 1 by 2, so root x. Okay. And what about root x? You will put on what? X is equal to L, yes or no? So here we have L, here we have root L, then resultant is nothing but root L. So C upon root L is nothing but what? It is again trying to help you that h x only. So can I write down that h bar is nothing but 2 times of h at x is equal to L? Got the idea? Yes. Okay. Now let us try to, okay, so then what will be your average this relation, like Nusselt number for any x, we have seen that Nusselt number at any x was written as 0.332 times Reynolds number at that particular x to the power 1 by 2 into Prandtl number to the power 1 by 3. Similarly, what I can write about Nusselt number at given L, or I can say that Nusselt number average. Then can I see that this is 2 times of this one? Then can I write down this is 0.664 into other things are same, yes or no? See how I am using x and L. I am using L here. Why? Because I am writing it for average one, and I have seen the average one is twice of h at any x, and given that your x is equal to L. Okay. So now I see the variation of Nusselt number for whom? For laminar flow I know. Okay. Now let us move to whom? The analogy between, is there any analogy between momentum transfer and heat transfer? So momentum transfer and heat transfer, let us try to understand that is there any process like just by knowing any one can you try to find out the other one also. So this is my logic. Okay. And if somebody is willing to know that what is the Nusselt number relation, this is valid for whom? For this one, the condition is that this is for Reynolds number less than what? 5 into 10 to the power 5. Then only you can apply these equations. Why? Because I am telling you repeatedly, this is valid for whom? Laminar flow only. And second most important thing about this one is that your Prandtl number is greater than 0.6 here. Similarly, if I go and write the relation for whom, for turbulent flow, then what does it look like is that your Nusselt number is basically, so your Nusselt number now, this is equal to 0.037 into Reynolds number to the power 0.8 multiplied by Prandtl to the power by. So this relationship is valid for whom? Turbulent flow. Okay, and what is this condition now? For this one, your Prandtl number range is what? Though your Prandtl number has started from 0.6 and it has traveled, okay, and your Reynolds number obviously is between 5 into 10 to the power 5 and between Reynolds number between 10 to the power 7. Your tau is your tau w is directly proportional to x to the power minus 1 by 2. This is one thing which we will be able to judge from here. Okay, so once I know my tau w is directly proportional to the x to the power minus 1 by 2, how we have done this? That you do du by dy, then you put y is equal to 0, and then what about delta? Delta is here is 4.91 into x upon root over rex. Why? Because I am trying to find out these things with respect to whom? With the respect of laminar flow only. And why we are analyzing laminar flow? Because laminar flow is easy to understand and analyze. Okay, now, so we also know that what is shear stress at wall in terms of skin friction coefficient. So shear stress at the wall in terms of skin friction coefficient is CFX, which is the skin friction coefficient, into rho into V infinity square by 2. What is V infinity here? Is your free stream velocity. And what is CFX? It is the skin friction coefficient. It is the skin friction coefficient. Okay, so now I know that tau w is like this one. Okay, then let us now try to analyze that can I find some relationship between these two? So then yes, I can do. So can I see, like let us go to the next. So let me erase this part. Then can I see that my tau w is, in case of when you put y is mu y is equal to 0 and du by dy at y is equal to 0, in that case what you will find out that this is equal to mu into v infinity into 3 by 2 into 4.91x divided by square root of whom v infinity into x into rho upon mu. And just now we have seen that tau w is equal to cfx upon 2 into rho into v infinity square. Okay, and then when you equate, let us say this is equation 2 and this is equation 1, and then when you equate these two, then what I am able to see is that my cfx upon 2, this must be equal to whom, 0.332 of into Reynolds number to the power minus 1 by 2. So this is one relation. Okay. Now, and I know that what is Reynolds number relation, or not Reynolds number, like Nusselt number relation with respect to Reynolds. So what is Nusselt number? Nusselt number at any given x is 0.332 times what? Reynolds number at x to the power 1 by 2 into Prandtl to the power 1 by 3. So can you see now that there is some analogy that can be fitted between these two? So let us see how we can do that. So now what do I do? That I divide Nusselt number divided by Reynolds into Prandtl on both the sides. So can I do that Reynolds number into Prandtl number I am dividing on the both the sides, then this is 0.332 and this is now became what? Reynolds number to the power minus 1 by 2, yes or no? And this has become Prandtl to the power minus of 2 by 3. So now I know few things from this fact, and then can I see that this is Rex only and this is Prandtl. So can you see that you can put 0.332 into Reynolds number to the power minus 1 by 2. Here we have same thing. So can you see that you can put this one as cfx upon 2. Okay, and then there is one dimensionless number who is the ratio of Nusselt number divided by product of Reynolds into Prandtl. This is called Stanton number. What is this? Stanton number. So Stanton number is the ratio of Nusselt number upon Reynolds into Prandtl. So I am writing down here now. So can I write down that Stanton number at the given x is equal to cfx upon 2? Can I write? Yes. Why? Because I have got this relation from here. So this is 0.332 times Reynolds number to the power minus 1 by 2. This is equal to cfx upon 2 multiplied by whom? Prandtl number to the power minus 2 by 3. So can I see now that I can see one relationship, like if I know just know the drag coefficient or skin friction coefficient, I can know whom? I can know h even sometimes. So can I see now that cfx upon 2 is equal to Stanton number at x multiplied by whom? This is 1 upon Prandtl number to the power what? 2 by 3. So this is Prandtl number to the power 2 by 3. So this is the analogy which is helping you to determine what is the relationship between what? Skin friction coefficient and skin friction coefficient. You are countering these when you are tackling the flow velocities, right? And then you are dealing with Prandtl number and Stanton number, these things when you are talking about heat transfer. So can you see that you are able to fix some analogy between fluid motion and heat transfer, and this relationship which you are able to develop here is called Rayleigh-Colburn's analogy. Okay. So this is called Reynolds-Kohlberg analogy. Okay. So sometimes they used to ask us that what is this analogy. So we will be able to answer that this is the Reynolds-Kohlberg analogy, who is able to correlate what? Correlate heat transfer and moment transfer. Can we see? Yes. Okay. Now, so let us now move to whom? Let us now move to whom? Force convection in flow through pipes. Like till now we have seen, till now we have seen what is the things when we are talking about the flow through pipes. Now we can see what is the flow through pipes. Yeah. Okay. So now let us see what are the things we are going to understand here. Okay. So flow through pipes. See, let us say there is a pipe. Okay, and in this there is some flow is happening. So what happens here is that if this pipe is subjected to some flow, and then this flow is also like this fluid is also having some temperature with it. Okay, so what happens here is that you have what, like at every point what happens is that your mass flow rate is constant, but one thing which is changing is the temperature. In what direction? In radial direction. Why? Because that once you are, let us say that you are flowing heat from, let us say that there is some certain heat flux which is given to this pipe, and then your fluid is gaining heat from this heat flux, and then this is traveling in this direction. Then what do I feel is that my fluid is having different temperature at every cross section. Yes or no? And moreover, you are having temperature varying in the radial direction as well, and this is obvious. Why? Because if you are at this point, then you are gaining directly in contact with the heat flux surface, but then this is decreasing. Then can you see that your T is function of R here? One thing is the, like here your temperature is function of radius, one thing, right? So now if you are trying to find out that what is the temperature exchange between, or not temperature exchange, what is the heat exchange between these 2 points, like let us say this is 0 and this is L, then your job is to find out that what will be the amount of heat transfer when there is some flow from this point to this point. Then what you will do is that this is nothing but m dot Cp into delta T. Yes or no? But what about this delta T? Which delta T you are going to take? This delta T, like delta T means T at this point, and let us say that T at the exit. Like let us say this is T at entry and this is T at exit. But what temperature you will take? Why? Because everywhere along the radial direction, everywhere your temperature is being changed. Then you will have to find out the bulk mean temperature at every hour. Then only you are able to find out that what is the temperature you are going to take here in this delta T. So my job is to find out now that what is bulk mean temperature. So what is bulk mean temperature? Okay. So let us understand what is bulk mean temperature. So this bulk mean temperature says that TB, like bulk mean temperature denoted by whom? TB. So TB at any given cross section of the pipe is what? That it takes into account the temperature variation in radial direction. The temperature variation in what? In radial direction. Okay. And where? At any given cross section. Don't forget that at any cross section it takes into account the temperature variation in radial direction at any given cross section. Got the idea? Then only I can say, otherwise this is not possible. Okay. So you are trying to find out TB at any given particular cross section. Then can I see that I can also write my Q is nothing but m dot Cp into what is that TB. Like this is the amount of heat is at that particular point. Yeah. And when flow is happening, then if I am able to find out delta TB, then I can say that okay, this is the amount of heat which has been exchanged. Got the idea? So let me now help you to find out that how to find out this TB. So now if you know that this TB, then how do you write down that what is your Q value? So total heat transfer rate is again nothing but m dot Cp into delta TB, right? Delta TB. So what is this m dot? M dot is constant anyway, Cp is also constant. And what is delta TB? Delta TB is TB at exit minus TB at what? Inlet. So this is your exit part and this is your inlet part. Then this is your inlet part and this is what? Your exit part, and you are gaining heat flux at these points. Yes. And then your job was to find out what is the amount of heat exchange. So can I write down that amount of heat exchange Q is equal to nothing but this one. So now I know how to find out the heat exchange when you are working with the what? Flow through pipes, right? So now let us try to find out the mathematical expression for TB. Like just now you know that okay, I will write TB exit, TB inlet, and what is this TB itself you will have to find out, right? So let us now find out what is TB. So how do we find out TB is like this. See, what I am trying to do now is that I am going to any cross section, like I am trying to draw any cross section, and at this cross section I am taking any strip. Okay, let me take this strip. Okay, and then what I will do is that I will analyze things about this strip, and then what happens is that I will integrate it, right? So can you see that what are the things about this strip? First thing is that we have some mass flow rate, right? So mass flow rate in this strip, and then we will integrate it, right? So at any given r, let us say this is what? This is dr. Then can I write down m dot is nothing but, or in fact dm dot, can I write down this is nothing but mass flow rate is density into what? Discharge, and this is density, and discharge is area into volume. And what is that area? 2 pi r into dr, the strip area. And what is that velocity? Velocity is, let us say, u. So now I know m dot, right? Then Then what is the thermal energy transported by fluid through this elemental ring? So what is the thermal energy transported? Then can I write down dq is nothing but dm dot into cp into t? Yes. So what is dm dot? This is rho into 2 pi r into dr into du into u, not du, into u into cp into what? T. Okay. So now what is the total energy transported at this particular cross section? Can you find it by integrating? And how you will integrate it? From 0 to, let us say this is varying from 0 to r. So what is the integration limit? 0 to r. So now I know that what is the what dq, not yes, dq at any given section. And then if you are able to find out the average one, and who is helping you to find out the average one? This tb, right? And with respect to tb, can I write down? Why? Because tb is taking care of all these things. Like here your t itself is function of r, here your t itself is function of r, and then you know that dr is there, and if you know the temperature as the function of r, then you can find out. Okay. So now can you see that with respect to tb, if I am willing to write, then can I write down again my q? Like if you integrate it, then you are able to find out q. So similarly here, what will be q at that particular section is nothing but m dot into cp into what? The bulk mean temperature, and these two should ideally be equal to each other. So when you equate these two to each other, like m dot cp into tb, and this is equal to 0 to r, rho times 2 pi r dr multiplied by u into cp into t as the function of r, then you will be able to find out tb. And now if I write down what is tb, then this is equal to 2 pi r into u. Like you will expand this m dot also, and then you will cancel out the common terms. Then this is 2 pi r into, not 2 pi r, the, like let me write it in better manner. So your t will be tb, in fact, like your tb, in fact, this is equal to 0 to r. Like this integration, you cannot get rid of this one. They will give you these values if they wish you to integrate it. Then this is 2 times r into u into t itself as function of r into dr divided by v mean into r square. How this came into picture? What you will do, that you will expand this m dot. And what is this m dot? M dot is nothing but rho into area, and area, the whole area is pi r square, the whole cross sectional area, and velocity is v mean, and this is cp into tb. So can you see that from this one and this one, so many terms are being cancelled out? Rho is cancelled out, pi is cancelled out, cp is cancelled out. So rho, pi, cp, if you cancelled out, then you write down the other terms, then your tb would look something like this. Okay. Then with respect to the flow conditions, we can have, like with respect to not flow conditions, like with respect to the boundary conditions, like how you are providing the heat to the flowing fluid, we have two conditions. One is called constant heat flux conditions. So in this constant heat flux condition, what I can see is that there is some pipe into which there is some fluid is flowing. Then what happens is that everywhere you are providing constant q everywhere, right? So this is the case of constant heat flux added everywhere. Then what happens is that whenever your fluid comes into picture, then this fluid, by traveling in this direction, will be gaining heat, right? Starting from this point, this will be gaining heat in this direction. Then if I try to draw what is the temperature variation, then can you see that I have entered at some temperature, and then my temperature has started significantly raising? Yes or no? Yes. So this is the case of whom? Constant heat flux condition. In constant heat flux condition, one thing which is constant is that you are providing constant heat flux, and when you are providing constant heat flux, then your surface temperature is not constant, rather it is increasing. Yes or no? Yes. So this is the case. How do we draw the temperature variations, right? And this is the bulk mean temperature which is increasing in the direction of flow. So what is this? This is the bulk mean temperature, TB, which is increasing in the direction of flow, and this is your wall temperature. Okay. So can you see that your wall temperature has, like, see, there is one called region called flow. Then what happens is that till certain point you will be feeling that your flow is not fully developed, means boundary effects are very much significant, and then you see that your flow is fully developed. So in the entrance region you can see that you are not entering into what, your equilibrium conditions, like your wall temperatures are still keep on increasing. Okay, so now till this point your wall temperatures keep on increasing and on, and then when you entered into fully developed region, then your surface temperature is remaining constant from this point onwards, and then what you are seeing is that your bulk mean temperature has started from this point, and then I can see that it has got increased. But there is one more thing, that this delta T which you can see here, after the fully developed region, this delta T remains constant. Delta T is constant when in the fully developed region. Okay, so in the fully developed region, in the fully developed region, what happens is that your delta T is constant. What? Got it? So see what happens here, like, let me summarize. Your fluid comes into picture, goes outside, so definitely this will be picking up the heat, and then this will increase its temperature. So this is not the issue, that yes sir, this will be varying. And second thing is that why you have shown variation like this one and this one, is that in the entrance region what happens is that you can see the entrance effect. So that is why this is increasing. What we can see that it is increasing in this direction, not in the manner when it is increasing in the direction of what, fully developed region. Got the idea? So this is about constant heat flux condition. Let's go to constant surface condition. Constant surface conditions means what? Your surface temperature, this one which you are able to see here now, this will remain constant. And if this surface temperature remains constant, then when my fluid will come into picture, then this will be picking away the heat, and this will keep on increasing. Yes or no? So yes, this is not that easy to imagine, not that tough to imagine. This is very easy to imagine, right? So your surface temperature is constant, and this happens in the case of what? Let us say some fluid is condensing. Okay, then condensation is happening at the constant temperature, and it has the good amount of heat into it, which it can give it to the other fluid. So what happens is that you are condensing some fluid at this region, then this condensing fluid has got what, constant surface temperature. Like this will not increase or decrease its temperature. Why? Because it is happening at constant temperature. So what you will be able to see is that your surface temperature is constant, and the fluid which is picking away the heat is increasing its temperature from the entrance region till the exit region. But now here your delta T is not constant. Here your delta T is not constant, rather it is, we can see, decreasing in the direction of flow. Okay, and this is the case of what? Constant surface temperature conditions. Okay, so can you see here that what is the TW here? Like surface temperature, this is not the function of x. Can you see here that your surface temperature is not the function of x, but in the earlier case we can surface temperature is the function of x. With the increase in x, surface temperature is increasing. Okay. Now, so these are two things. So whenever you are working for the fully developed region, for the fully developed region, for the fully developed region, for the fully developed regions, for the fully developed regions, what happens is that your Nusselt number is constant. And what is that Nusselt number in case of, like, let me erase the other rings. So what I am writing is that for fully developed flow, so for fully developed flow, your Nusselt number is constant, and this is equal to 4.36 when you are working with dq is equal to constant or constant heat flux conditions, for constant heat flux. Got the idea? So we should remember this fact. Sometimes they directly ask us that what is the Nusselt number in case of constant heat flux condition. Similarly, we have Nusselt number. This is equal to 3.66 for what? 3.66 for whom? Constant temperature conditions, for which case this one, this is valid for whom? Constant temperature conditions, or what constant wall temperature conditions. Okay, so this was all about what? Heat transfer by convection through what? Through the flow into a pipe. Okay, now let us quickly understand what is free convection. So free convection is not that tough to imagine. So free convection, we have just talked at the start of this lecture, we talked about it, right? And let us now quickly see the few facts about free convection. So in the free convection, like H we have seen in case of forced convection, so in the free convection, H is function of whom? G, gravity, beta, delta T, L, mu, rho, Cp and K. Why this is dependent upon G and beta and delta T? Why? Because your density changes are very much dependent upon this, and flow conditions are also dependent upon the gravity. So that is why now my flow conditions are dependent upon these factors also. So what is beta? Beta is telling you that it is telling you that how much volume can be expanded. So it is the isobaric volume expansion coefficient. What is this? Isobaric volume expansion coefficient. This is isobaric volume expansion coefficient, and how it is denoted? This is denoted by 1 upon V into delta V upon delta T at what? Constant pressure. Why? Because this is the isobaric expansion coefficient. And what is the unit? Its unit is per Kelvin. So for ideal gases, beta is equal to 1 upon T. For ideal gases, beta is equal to 1 upon T. Okay. And what about what you can think about this beta? That if your beta value is higher, like if your beta is higher, then your delta V is also higher. If your beta is higher, then your delta T is also higher. Okay, so this is one fact. Okay, then what is L? What is L? L is the characteristic dimensionless number, not dimensionless, characteristic dimension. So what is L? L in case of free convection is, L in case of free convection is bit different with respect to what? Forced convection. So for vertical plate, let us say I am trying to analyze the heat convection from a vertical plate. Okay, like let us say that plate is of this direction, then this is your characteristics. dimension L. Okay, let us say you are talking about a vertical cylinder, then what is your L? Its length. Okay, and let us say you are talking about a horizontal cylinder, then what is the characteristic dimension? This one. This is your characteristic dimension. And then what about flat plate? Like your flat plate is in horizontal direction, then your L is nothing but, if this is A, this is B, then L is equal to A plus B by 2. So what I am helping you to know is that what is the characteristic length in case of free convection heat transfer. So now L very much depends upon whom? Very much depends upon that how your object is oriented, right? And now what is this dimension for a sphere? For sphere it is the diameter of sphere. Okay, this one. And for horizontal, this d is helping you to, like I am writing, the diameter is equal to the characteristic length. So this you should know, then only you will be able to solve. Now so like in force convection, like in force convection we have Reynolds number, which helps us to understand what is the nature of flow, whether it is laminar or turbulent. Similarly here we have Grashof number, which helps us to understand that whether the flow is laminar or turbulent. So what is this Grashof number? So your Grashof number, this is equal to what? The ratio of inertia into buoyancy forces, the ratio of inertia into buoyancy forces, divided by the viscous forces whole square. Viscous force, the whole square of viscous force. Then when you solve this one now, then you are reaching to your Grashof number GR. This is equal to G beta mu square. Okay, we know about all of this. G gravitational constant, beta is the isobatic, volumetric constant, is the characteristic dimension, and mu is the kinematic viscosity. Okay, so this is Grashof number. So Grashof number is analogous to whom? Reynolds number. Reynolds number. So this question is very, we will ask you that become the following number in free convection is analogous to forced convection. So what you will find that Reynolds number is the one. Okay. Then what is the Nusselt number here? So Nusselt number is again here the function of whom? Grashof number and Prandtl number to the power n. Okay. So Nusselt number is some constant into Grashof into Prandtl to the power n. Okay, and one more thing here we need to understand is that n value is decided for certain kinds of flow. So n value is 1 by 4 if the flow is laminar, and n value is 1 by 3 if this the flow is turbulent. Okay, so but we have not till now got the idea that how you will decide that flow is laminar or turbulent. So this is decided by which factor? A factor called what? Rayleigh number. What is that Rayleigh number? The product of Grashof number into Prandtl number. So let us understand Rayleigh number. So Rayleigh number, this is equal to what? This is the product of Grashof number and Prandtl number. So when your Grashof number into Prandtl number, when this product is less than 10 to the power 9, then you say that flow is laminar. Okay, and when your Grashof into Prandtl number, this product is greater to 10 to the power 9, then you say that your flow is turbulent. Okay, so this is all about free convection. So now I know most of the things about free convection. Like, what is that? That my free convection heat transfer coefficient is function of what? G, beta, delta T, L, mu, rho, Cp and K. That is beta from the thermodynamics. This is isobaric volume expansion coefficient. This is 1 upon V into delta V upon delta T at some pressure is equal to constant. And for ideal gases, beta is equal to 1 by T. So this is the dependency of H. And then L is nothing but for the various orientation, this is getting changed. For vertical plate, this is the length. For vertical cylinder, it is length again. For horizontal cylinder, the diameter is the characteristic length. For the, let us say that if I have drawn what slab here, for slab length is nothing but the A plus B by 2. Okay, and for the case of sphere, what is the characteristic length? Characteristic length is nothing but diameter. And then I know that Grashof number is the one who is helping us to decide that whether the flow is laminar or turbulent. And now in this one, my Reynolds number, Nusselt number is function of Grashof number and Prandtl number, and then I know that what is Nn, and for what laminar and turbulent, and then I know when your flow will be laminar and when your flow will be turbulent. See, the question from convection area will be always like they will expect you to find out that they will give you certain variables and they will be willing you to find out that can you find the correlation things and other things, right? So you should be able to do. Okay, so let us finish this topic, and then you will be certainly able to solve the questions if you are following. Okay, so fine, we will stop here.